In my last example, we looked at what happens when an artificial satellite orbits the Earth. Let's now continue outwards into the universe. Once again, the law of universal gravitation truly is universal, so we could use it to tackle some rather big questions. Let's take a look at the next problem. Next problem says, estimate the number of stars in the Milky Way galaxy. The sun is about 30,000 light years from the galactic center, and it completes one orbit in 250 million years. How we know those numbers is a really long story. For those of you that are going into college next year, for example, I would highly encourage you to enroll, when you do, in an introductory astronomy course. You will find the course very easy. If you have a good instructor, it will largely be qualitative. You will get a lot out of that course. For those of you that are not seniors, you may want to consider in the future enrolling in my Independent Study Astronomy AB course. You will get that information, for example, in that course as well. Now, a light year. A light year is not a unit of time. It is a unit of distance. It's the distance that light travels in 1 year. It's about 6 trillion miles. It's about 9.5 trillion kilometers. Just to give you an idea, the distance that the sun is from the galactic center is about 30,000 light years, and it takes about 250 million years for the entire solar system to complete one orbit about the center of the galaxy. What we're going to do is estimate the number of stars in the Milky Way galaxy, and we'll assume that a typical star has the mass of the sun, which is 2 times 10 to the 30th kilograms. Now, if you are unfamiliar with the basic layout of the Milky Way galaxy, let me give you a short primer on the basic layout. The Milky Way galaxy is an example of what is called a barred spiral galaxy. So first of all, there is a long bar of material like so, where right here is the galactic center. Now, what is the material? The material is basically 3 things. It's stars, dust, and gas. Okay, now what is the dust and what is the gas? The dust and gas is basically the same thing. It's mostly hydrogen, some helium, and a scattering of basically everything else on the periodic table. If the material is cold, it's dark, and it doesn't emit any light, that's referred to as dust. However, if there are nearby stars, those nearby stars can ionize some of the atoms associated with the dust. When this happens, those atoms emit light. That's referred to as gas. So the dust and the gas is basically the same stuff, if you will, just at slightly different temperatures. And then, made of hydrogen and helium and a scattering of everything else on the periodic table, you have stars. And then trailing off symmetrically from either end of the bar, there are 2 enormous spiral arms, which are made of the same material, stars, dust, and gas. That looks like this. Here. And here. So if you look at the Milky Way galaxy face on, it kind of looks a little bit like a pinwheel. And then in between the 2 major spiral arms like so and the galactic center and the bar associated with it are several other smaller spiral arms. I'll just kind of draw them a little bit like so. Okay, now where is the sun located? The sun is located, let me kind of make this a little bit neater here. The sun is located about 2/3 of the way out from the galactic center on kind of like the inside, if you will, of one of the minor spiral arms. This minor spiral arm is referred to as the Orion spur. Here's the location of the sun. The next spiral arm inwards over from us passes through the constellation of Sagittarius. This is referred to as the Sagittarius arm. Now, the distance from one side of the galaxy to the other is about 100,000 light years. The Milky Way galaxy is 100,000 light years wide. Now, to give you a little perspective of how you can actually see this, you have to, of course, go far away from the city lights to be able to see the Milky Way. Some of you may have perhaps been able to see the Milky Way on a family vacation out to the mountains or the desert. You have to get away from the city lights in order to see the Milky Way. If you do this in the summer months, So if you take a family vacation out to the desert, for example, or the mountains during, say, June or July, and you see the band of the Milky Way passing across the sky, you're actually looking in this direction towards the galactic center. What you're actually seeing pass across the sky is the next spiral arm over from us. That's the Sagittarius arm of the galaxy. However, if you do this in the winter time, say 6 months later, so you take like a ski trip, for example, in December or something like that during winter break, you'll see the band of the Milky Way going across the sky, but it is much less diffuse, or much more diffuse, excuse me. In other words, it's dimmer and thinner looking. Well, when you do this during the winter months, you're looking essentially 180 degrees away. You're looking in this direction like so, through the Orion Spur, and then outwards away from the galactic center. So in the summer, you're basically looking in this direction at night. In the winter, 6 months later, you're looking in this direction at night. And then during the spring and autumn, when you generally can't see the Milky Way very easily, you're looking perpendicular to the plane of the galaxy, like so. Now, this is what the galaxy looks like if you could see it face on. If you can see it, however, in profile or tipped on its side, then it looks a little bit like a fried egg. Instead, you'll see something like this, or it looks rather something like this. Like so. Where the bar is located and near the galactic center, this is referred to as the Galactic Bulge. And then here and here, basically the sides of the galaxy up on the top board, this is referred to as the galactic disk. And then right here, once again about 2/3 of the way out from the center, this is where the sun is located. Distributed, by the way, in a spherical halo around the galactic center like so, are a series of enormously large star clusters called globular clusters. Incidentally, by the way, I provide for you in today's folder a detailed screencast that goes through the structure of the Milky Way galaxy and shows you pictures associated with what I'm drawing here. That screencast is presented to you as an Ed puzzle for you to complete a little bit later on. Okay, now getting back up to the top diagram. Let's assume very simply that the sun orbits the galactic center in uniform circular motion, just to make the problem simple and straightforward, like so. And then right here is the distance between the sun and the galactic center. This distance here, small r, we'll call it, is given to us as 30,000 light years. In addition to that, we're also given the orbital period of the solar system itself. It's about 250 million years. Approximately once every 250 million years or so, by the way, the solar system passes through one of the spiral arms of the galaxy. This coincides roughly with mass extinctions on the Earth. I described this a little bit in my screencast. Once again, you are to watch that screencast. Okay, now just simply using Kepler's third law, here's basically what we're going to do. What we'll use Kepler's third law for is to come up with an estimate of the mass of the galaxy. We'll think of the entire mass of the galaxy here as a point at the galactic center, just to keep things simple. And then once I have that number in terms of kilograms, we'll then compare that number to the mass of a typical star, such as the sun. Therefore, this will then allow us to come up with a ballpark estimate of the number of stars that make up the Milky Way galaxy. Okay, so now let's go ahead and move here to the lower board, and now let's start to crunch the numbers. Okay, so first of all, here's what Kepler's third law is going to look like for this situation. Like so. T squared is proportional to r cubed. We've seen this equation before already in a couple of problems. The only thing that's different, however, is the mass in the denominator of the expression. Now it's just the mass of the galaxy. So let's go ahead and cross multiply now and solve for the mass of the galaxy. Like so. And now I get to some rather crazy numbers. So let's take a look at small r first. That's given to us as 30,000 light years. As I mentioned a little while ago, 1 light year is about 9.5 trillion kilometers. That's 9.46 times 10 to the 15th meters per light year. Let's go ahead now and convert 30,000 light years into meters. Okay, so this is how many meter sticks you would need laid end to end to go from the sun to the galactic center. So it's gonna be a lot. So let's see, 30,000 and then multiply by 9.46 times 10 to the 15th meters per light year. And this is about 2.84 times 10 to the 20th meters. Okay, and then we have capital T. Capital T is 250 million years. That's 250 times 10 to the 6th years. We need to convert this into seconds. So I'm going to multiply by 3.15 times 10 to the 7th seconds per year. Okay, we've seen that conversion factor before as well. So 250 times 10 to the 6th, and then times 3.15 times 10 to the 7th, and that comes out to be about 7.88 or so times 10 to the 15th seconds. That's 250 million years in terms of seconds. And then along, of course, with capital G, okay, for reference here it is once again. Let's now go ahead and plug everything into the expression and then come up then with an estimate of the mass of the galaxy in terms of kilograms. As you'll see, it's going to be quite a bit. All right, now I still have capital T in my calculator, so let me go ahead and square that, multiply that by G, like so, put it up in the numerator. All right, times 4 times pi squared, and then times 2.84 times 10 to the 20th raised to the 3rd power. And then when I make all of these calculations, the mass of the galaxy turns out to be about 2.2 or so times 10 to the 41 kilograms. And now we'll compare this to the mass of a typical star, such as the sun, to come up with a ballpark estimate of the number of stars that make up the Milky Way. Okay, so the number of stars that makes up the Milky Way then is going to be this number here, 2.2 times 10 to the 41 kilograms. And then what we'll do is we'll divide it by 2 times 10 to the 30th kilograms per star. That's the mass of the sun. Notice that the kilograms cancels out, and I'll end up with something in terms of stars. So divide by 2 times 10 to the 30th, and I then end up with the following. It's about 1.1 times 10 to the 11th stars. That's the same thing as 110 times 10 to the 9th stars. And a 10 to the 9th is a billion. So we're talking about several hundred billion stars. This is typical of spiral galaxies. When we look out into the universe and we count the number of stars associated with typical spiral galaxies, we come up with these types of numbers, several hundred billion stars. Now this calculation, of course, is an estimate. It is not exact, but it is certainly within an order of magnitude. In other words, it's probably pretty close to the actual value. But it doesn't take into account a couple of things. First of all, it actually doesn't take into account the material that is further from the galactic center than the sun. So the estimate that I made is low because of that. In addition to that, it also doesn't take into account a single object that resides at the galactic center that some of you may have heard of, what is referred to as a supermassive black hole. We'll take a look at the supermassive black hole in the next example. As I conclude this video, however, once again, make sure that you watch the screencast that I've posted for you on the structure of the Milky Way galaxy.